Hello everyone, welcome to this fourth session of the season 5 of the EDHEC speaker series, The Future of Finance. I'm Emmanuel Jurczenko, Executive Director of Graduate Finance Program. It's my pleasure to introduce today Professor Rama CONT. So we are very happy to have him in this series. Rama is a professor of mathematics at the University of Oxford. He's the head of the Oxford Mathematical and Computational Finance Group. He's a very prolific researcher in quantitative finance. His research expertise covers stochastic analysis, stochastic processes, mathematical finance. He has co-authored more than 80 research papers published in quantitative finance, mathematical finance. He's also the editor-in-chief of Mathematical Finance Journal. And today, Rama will talk about risk management and hedging with generative models, how to use generative models to try to develop advanced data-driven hedging strategies. So we are super happy to have him today. And before I leave the floor to Rama, I want also to thank to the two co-moderators of today. First, Professor Lionel Martellini, Professor of Finance, and a bright student of our MSc in Financial Engineering, and also a double diploma with the University of Côte d'Azur, UNICA, in Mathematical Finance, Antoine Blaise. So without further ado, Rama, the floor is yours. Thank you very much.
Yeah, thank you very much, Emmanuel. Can you hear me well?
Yeah.
Okay. So I would like to talk about generative AI and some applications to risk management. So I entitled the talk Harnessing Generative AI for Risk Management, and you will see why. And this is based on joint work with several students and co-authors. I will mention the papers in the slides, and I think you will have the links to the papers if you want to go into more detail. Okay, so this is the outline of what I will try to present. First, I will talk a little bit about generative models, what they are, and why they're interesting for risk management. And then I will try to spend a few minutes on methodological challenges for using generative AI in finance. This is a very interesting topic, which is currently being discussed in all financial institutions, how to use generative AI to improve productivity and to improve the processes that we encounter in financial risk management. So I'll spend a few minutes on that. And then I will outline two applications of generative models. One is using generative models for scenario simulation. And the second one, which uses the first one, is how to design data-driven hedging strategies with generative models. So as I mentioned, this is based on several research papers, all of them recent, 2024, 2025, with some of my former students and postdocs. You can see the titles here. They can be easily found online on SSRN or my website. So if you want more details, I refer you to these papers. Okay, so what is generative AI? So everybody has heard now of Gen AI because of ChatGPT. And well, unfortunately, this leads to a confusion and people think that generative AI means large language models. This is not the case. So generative AI pre-existed large language models. It refers to a category of machine learning algorithms that are designed not to do pattern recognition or execute a certain task, but they're designed to generate or simulate outputs which are similar to, but not identical to, data which they're trained on. So it means that you have a large database, for example, of images of animals, let's say, that's the first application which was done historically. and you want to train your computer to generate new pictures of animals. So a generative model is an algorithm that does exactly that. It learns from your database to extract the main features of the elements composing your database, and then it generates outputs which have these features. So and here the inputs can be anything really. It can be images, text, video, numbers, arrays, or human speech specimens, voice, whatever you like. And as long as these inputs have something in common, which you may not be able to model explicitly, but as long as there is something in common, the algorithm tries to extract what's in common and then reproduce those common features in the outputs. Okay? But so for those who have studied simulation, and maybe you have studied simulation in your courses, you can describe generative models as non-parametric data-driven simulation algorithm. What does that mean? I'll come back to this in the next few slides, but it means that in the traditional approach to simulation, you have an explicit statistical model of something. You have, for example, you assume the data has some specific distribution, Gaussian or something else, and then you estimate parameters of that distribution from the data. Now you have a distribution with parameters specified. The formula for the distribution is known, and then you generate samples from that with some algorithm designed for simulating that specific distribution. But you know exactly what you're simulating. Here, the idea is, I don't know exactly what I'm simulating, but I have samples from it. I just know that I want the same. I want something like the sample, but I cannot write a formula for what I'm simulating. So I cannot write a formula which tells me if I give you an image, compute this formula and tell me if this is a dog or a cat. We don't have that. But if I show you a dog or a cat, you can recognize that picture. So the idea is, if I have data, can I learn a little bit like humans learn to draw and generate similar outputs? So that's what these algorithms do. And so there are a variety of generative models which do this task. In the chronological order in which they're developed, you have variational autoencoders, generative adversarial networks or GANs, generative pre-trained transformers or GPTs, including ChatGPT. And then more recently, you have other models called score-based diffusions. This is behind the tool in GPT-4, which is called Sora, which makes videos and so on. So all these are trying to do the same task, but they do it with slightly different algorithms. And behind each of these algorithms is a neural network, which is trained on a large data set to learn the features of the data set and then simulate things which look like the data set. The difference between these algorithms is in the way the neural network is designed, the so-called architecture of the neural network, how many neurons and how they're connected. And second, how the neural network is trained. So the training and the architecture is what distinguishes these algorithms. So these algorithms were developed initially for image and text simulation. But immediately, people who work in finance saw the potential of using these in finance. And so they have been progressively deployed in finance. We wrote a report in 2023, published in the MIT Technology Review on the potential for generative AI in financial services. And so we outlined in this report, which you can find free online, what are the potential use cases for this technology, which was emerging at that time, and also some of the potential challenges in deploying this. I will now describe a little bit some of this. So, but now just to put generative models in perspective, here I really want to emphasize that generative models are nothing else but simulation algorithms, but They are simulation algorithms which learn to simulate from data. So in classical model-based simulation, you have, for example, a time series model or some formula which looks like this: xt plus 1 equals g of xt, yt, epsilon t. Xt, yt are past observations. Epsilon t is some random variable, some noise input. And your model looks like this, where g is a known function. It's, for example, if g is a linear function, then this is a Rama model. You have maybe studied linear models in statistics. So to simulate a model like that, well, you need to specify the function g. You need to specify the distribution of this random variable epsilon t. And the way the simulator works is this: you simulate, you need something called a random number generator. It generates independent outputs with the distribution that you want for epsilon. And then you put the random number generator's outputs in this formula instead of epsilon. And then you calculate the next value of your time series, and then you go on. So the epsilon has a known distribution, which you specify. The g is a known function, which you can estimate from data. And then you apply this calculation in which everything is known to simulate the next value. And the epsilon is the output of a noise or random number generator. So this is how you simulate, for example, time series models like ARMA or GARCH. In a generative model, the idea is exactly the same. You do the same steps, except that now you don't know g. So g can be a complicated unknown function. It's not necessarily a linear function. It can be something you have no idea what it is, but you still want to learn to simulate your data. So the idea is you represent the function g as a neural network, and you try to learn the coefficients of this neural network from the data. So it's exactly the same structure, but now the function g is replaced by a neural network, and it's now called the generator. So instead of simulator, they say generator, but it's really simulation. But it's now simulation where the algorithm learns to identify the function g or the generator from the data. So how does that work? Well, so the function g will now be represented as a neural network. The neural network has some hidden parameters or weights. Let's call them theta. And so if you assign just any value to these parameters theta, the neural network will output nonsense. So it's not going to stimulate what you want. So what you're going to do is you will change this parameter theta iteratively such that the output looks more and more like the distribution of the data that you're training on. So the way you train this neural network is you do a lot of iterations. At each iteration, you try to change the parameters of the neural network a little bit such that the output distribution is closer to the data distribution in your sound sample. And the idea is that if you iterate this many, many times, maybe you will get closer and closer to the distribution of your data. The outputs of this algorithm will look more and more like the distributions of your data. And the way you change this parameter iteratively is you look at some measure of a distance between the output distribution and the data distribution. So here you need to have some notion of distance between probability distributions. If you have such a notion, then for each output distribution, you can quantify how close you are to the target. And if you are, and then you change the parameter a little bit to get closer with the gradient descent method. So that's the way all neural network algorithms are trained. But here the objective is to have an output distribution which looks like the inputs, looks like the data distribution. So that's the goal, rather than doing pattern recognition, classification, or executing certain tasks like in other applications of neural networks. So that's the idea. Now, this idea is very general and has been applied to various types of data, as I mentioned. The most famous being texts, human language text. So there, the model learns to generate text, but you should understand that it's really a surprising application, because in this approach, you view the inputs, the thing you train on, as a bunch of random variables, really. So, for example, if you look at pictures of dogs or cats, you look at the pictures as a sample from a distribution which happens to be concentrated on pictures of dogs or cats. So you look at this as a samples from some statistical distribution. And the same way you look at text as basically random sequences of characters or words, which happen to be ordered in a certain way, which makes sense to humans, of course, but the computer doesn't really care about that. It's not, nobody hard codes the grammar or meaning or anything in this algorithm. They just treat the inputs as some sample from a very large distribution, and they just try to figure out the probabilities for one word or one group of words to follow the other, and then just in the output, they just try to maximize the likelihood of this sequence of words occurring. So it's really surprising, and a linguist should really be depressed to see that by looking at language as a random sequence of words, you get outputs that are more efficient than, for example, 40, 50 years of structural linguistics, which tries to hard code how language was actually structured and then code this into computers. That approach didn't work, and this approach, which treats everything as statistical, seems to be more efficient. So this is so general that you can throw any kind of data at it and then see if it can learn to detect the structure and generate similar data. And people have tried this. They've tried this for a structured data, meaning sequences of numbers. In finance, there's a lot of that, price returns, interest rates, foreign exchange returns, that kind of thing, but also unstructured or heterogeneous data, balance sheets, central bank interventions, speeches by central bankers, sentiment analysis from social media. Can you extract things that have, some, there's all sorts of interesting applications here. So I'm going to describe one type of application, which is to use this technology for scenario generators, or in other words, simulating the financial scenarios for prices, interest rates, or other financial variables. And in the computer science literature, they call it synthetic data. But really, synthetic data is nothing else than simulation, something we've been doing in finance for years, but except that in this literature, everything is rebaptized with new names, so it sounds new. Anyway, so scenario generation is the following idea. Let's say you want to simulate scenarios for a bunch of variables, prices of stocks, interest rates, foreign exchange rates, whatever you think is interesting for your portfolio risk management. You take a large enough sample of these variables. Obviously, here we are limited by existence of data. We cannot go back 10,000 years and have millions of data points like they have in images or in online applications. So here, if you look at historical data, you're limited by the history. However, in some applications in finance, there are two areas in which there's lots of data, typically millions of data points. One is retail finance. For example, if you're doing credit scoring or loan pricing or credit card, scoring and so on. There you have millions of customers if you're a bank, so you have access to millions of data points. Another application where you have millions of data points, even more, is high-frequency finance. If you're doing high-frequency trading or even medium-frequency trading at the level of minutes or seconds, you still have a lot of data points to learn from. So the idea is that you have such data sets, but they're complex. So it's very difficult to build explicit statistical or econometric models of this data. And people have tried the idea to say, well, what if we throw these animals, these generative models on the data? Can they learn the structure and can they simulate more efficiently than the good old econometric models? Can they compete with them? And so this is what we did in these two papers. One of them is with my former student, Milena Vuletic. We looked at implied volatility surfaces, so something which has a rather complicated structure, a multivariate structure with two dimensions. Can it learn to model the dynamics of these complicated objects? And another one was to learn to simulate tail risk scenarios for portfolios. I will speak a little bit about that. So as I said, there are different types of generative models. The difference is in the architectures of the neural networks inside them and the way they're trained. So let me say a few words about training. So as I said, training means here you take a neural network with some hidden coefficients or weights inside, and you iteratively update the coefficients such that the output of the neural network, the generator, looks more and more like the data. Okay. But here there was a very interesting development in 2014 by Jan Goodfellow and co-authors. So their idea was to say, well, if you train one neural network, this is an optimization problem. So you optimize the weights such that the output is what you want. But we can do it in a slightly different way. And this is called adversarial training. So the idea is that, well, children or students learn better with a professor. So here you have your very good professors who are watching the talk, so they will not say the opposite, I guess. And so the idea is that here, well, in machine learning, you can introduce this idea of a tutor or a supervisor who is teaching you in some way, is correcting your errors as you go on. So the idea is instead of one neural network, we're going to have two neural networks. The generator is trying to learn to generate scenarios, and the other one is called the discriminator. Obviously, you would not use this terminology in an academic context, but you would call it tutor or professor. So this discriminator is going to verify the output of the generator and give it a score. So what is the score? The idea is that the generator is trying to simulate outputs which look like the data, the real sound samples. So the discriminator is going to compare the outputs of the generator to the real data. And if they look alike, if the output looks like a sample from the real data in terms of its likelihood of being from the empirical distribution, it's going to give it a high score. So if the high score means it's a realistic output, low score means it's not realistic. And so this discriminator is going to actually give a feedback to the generator. So this, and they are going to be trained simultaneously. So at each iteration, the generator generates some output, the discriminator gives a score, good or bad, or something in between 0 and 1. And then based on this, the generator is going to update its output and so on. So you get this, you train this, these two networks in tandem. And in this way, the generator learns to produce output that is statistically closer and closer to the data as certified by the discriminator. And the discriminator is simultaneously learning to give more and more refined and precise scores. So this is called adversarial training. It's really trying to mimic the paradigm of a student and a tutor, and the tutor keeps correcting the student. And the idea is that children learn like this by repeating, and then somebody tells them this is correct, this is not correct, this is good, this is bad, and they try to embed this into this algorithm. So and this really is an idea which has proved very interesting. So it's just a way of training neural networks, but instead of training one network, you train two, and at the end you have two for the price of one. And the discriminator is usually something used in the training but then thrown out. But in fact, here we will see that it's actually an interesting thing for applications. So why am I describing this adversarial networks, adversarial training, or GANs? Because GANs have been the ones which have been the most widely used in finance. They have been used to build market simulators in the way that I described. So people took these architectures which were available in the public domain. They just trained them on asset returns, and they said, okay, here we have a market simulator. And so here is a list in this table. I have a list of references of people who did this on financial data. The algorithms used in these papers were not new. They were the same algorithm used for simulating images. They just ran them on financial data, said, here you are. Here you have a market generator or market simulator. So when you do this training, the end result is a black box, really, because it's a neural network, which in principle has been trained to simulate things that look like your data, but you don't really know how it's doing it. It's somewhat a mystery. So the only thing you know is that it has tried to minimize some distance between the output distribution and the data distribution. But okay, so and one of the challenges in this area has been model validation. So what is the model validation challenge? Well, in the early applications, which are image generation, you had a situation like this. On the left, you had pictures of true dogs, and then you train a model to generate dog pay pictures on this database, and it generates things like the ones on the right. These are pictures, generated pictures of dogs. They are not pictures of any real dog. They are pictures which look like dogs, but they're not actual dog photos. They are completely computer-generated images, but they look pretty realistic. Occasionally, you will have the dog with 3 eyes or 4 ears or whatever, but nobody really cares because it's image and, people find that funny and so on. And here, in this context, model validation is easy. Any user can look at this and say, oh yeah, that looks like a dog, or that's not realistic, or this is realistic. Even a kid can do that. Even a dog probably can do that. So in this case, model validation is easy. Even dogs can do it, because the only thing you need to do is look at the image and see if it's realistic. Now, if you go to scenario generators for stock returns, it's less trivial, because the output will look like the one on the right here. It's going to be a bunch of curves with different colors. Each one is a different stock. Okay, now I tell you which one are these realistic scenarios for this stock or that stock, NVIDIA or S&P 500 or whatever. Well, who knows? I mean, you can't do it by looking at this figure. You have to check a lot of statistical properties and so on. So clearly, validation by user perception is not possible. And here I just draw 5 graphs. Typically, you will want to simulate scenarios for your whole portfolio. The whole portfolio will be 1,000 stocks over the next 252 days. So it's going to be 252,000 numbers in a matrix. Okay, nobody can look at that. It's horrible. So you need a method for validating that output. It cannot be done by hand. So you need an algorithm for doing this. And it's not clear how to do the validation here. And this has been one of the stumbling blocks of adoption of these methods in banks, for example, because in banks, there's something called model validation. If you deploy a new model or algorithm, somebody upstairs has to approve it. and they have a list of criteria, check the assumptions, check this, check correctness of the algorithm. Here, it's a black box. So check the assumptions. Okay, where are the assumptions? There's no assumption. You don't know what they are. So it's this has been really a stumbling block. It has also been a stumbling block for the adoption of generative models in other areas like healthcare, because they're also the decision maker needs to understand if the model says something, what is it based on? If they don't understand, they're reluctant to do that. So this is a very interesting problem. But the other problem is the following. So I didn't go into detail, but the way you train the models is you, as I said, you look at some distance between the output distribution and the data distribution. This is a statistical distance, which tries to say if two distributions are close or not. It's typically computed using entropy or Kullback-Leibler divergence. This is a notion of distance between probability distributions, which is obtained by averaging some loss function across the sample. So by nature, the way these distances are constructed, they're averages across the entire sample of some loss function. They are dominated by typical values of the sample. So if you have lots of data in one region and very few in another region, the distance will be dominated by regions where there's more data, just because you're averaging across data and you give the same weight to all observations. Now, this is okay for image simulation, because if you have lots of dog images, okay, some dogs will look very different in the database, but you typically don't care about that. You want the algorithm to simulate a typical dog. So if occasionally you have very strange dogs in the database and it doesn't learn to simulate those, nobody cares. But here, it's really the opposite, because if your observations are the returns of some portfolio, well, if you only learn to simulate the typical returns, which are fluctuations of 0.5% around plus or minus 0.5%, and you leave out the atypical fluctuations, which are the days where the market crashes or rallies, well, that's too bad, because in the risk management, you're mostly interested in the ones which are atypical. So in fact, in risk implications, one is primarily interested in so-called tail scenarios, which are the very large and very small movements in the portfolio. And typically the major risk or the major components of the return of the portfolio over a year will be concentrated in a few days where there are large moves. So if your algorithm doesn't catch those correctly, if it only catches the 0.05 movements, it's really not interesting. So this is a bigger problem, because it means that the way these algorithms are trained is not sensitive to this tail scenario or risk-bearing scenarios. And that's a problem, because we want those to be captured in the simulation. So for this reason, we think that taking off-the-shelf generative models and just running them on financial data, as many people have done in the past, is not necessarily a good approach. There's no guarantee that the simulator you get in this way will correspond to what you want. It may not capture the essential features of financial data that you care about for risk management. It will generate pictures with figures and nice colors, but when it comes to validation for risk management, it may be actually quite poor. So here I'm going to describe an approach. So what I'm saying is that if you want to use these things in risk management, you need to understand how they work. You need to go under the hood and redesign some of the training mechanisms to adapt them to the objective of the end user, which is to use them, for example, for portfolio risk calculation or hedging or whatever. Okay, so I'm going to show you how to do that in two examples. So the first example is what we call tail GAN. It's an algorithm which adapts the GAN method, so the generative adversarial training, to train a neural network to simulate scenarios which respect the tail risk of a certain portfolio. So we don't want to lose sight of those tail scenarios. So we don't want to just train them to match average or typical scenarios. We want to make sure that we capture the tail risk in a simulation. So how do we do that? So the idea is an idea which is quite generic in machine learning. The idea is you identify the features of the data which are important to you. So feature can mean any property, but you need to define it mathematically in a way that you can code in a program. And then you compute those features, and then you train the machine learning algorithm on those features instead of training them on the raw data. Okay, so here the raw data is you have matrices of returns of stocks or indices or whatever you put in your portfolio. So if you have n assets over t days, you have n by t matrix. It can be huge. So these are the kind of inputs you have. But what you care about is really the loss distributions of some portfolios. Okay, and in fact, if your simulated data and the historical data give you the same distributions for the portfolios that you use, you're happy. So this is the only thing you care about, really. So it means that you don't really want to match sequences of numbers. That's not the goal. The goal is from these sequences numbers that are the returns of the assets, you construct certain returns of portfolios, you aggregate them with trading strategies. So if they're constant portfolios, it's just a linear combination. But if they're not constant portfolios, if they're more complex strategies which involve state-dependent, price-dependent, time-dependent weights, then okay, there's some rules that to construct a portfolio. You follow these rules, you build your portfolio, and over each time period, you will have a portfolio return. Okay, so and now the portfolio will have a loss distribution, and this portfolio loss distribution is a one-dimensional distribution. So the initial data can be very high dimensional. It's number of assets times number of time steps, but so this can be thousands or even more. But when you take a given trading strategy and you run it across the scenario, it gives you one number. The gain of that strategy is one number. So it's a one-dimensional observation. So each strategy will project your data into one number, which is the gain of that trading strategy. And if you have k such strategies, you will get k such projections. And those are the things you care about. You care about the gains or losses of these k portfolios. So the idea is that the features I care about in financial data are really the gains or losses of portfolios. And they have a financial interpretation. They correspond to a value in euros or dollars, and I can attach a meaning to them. Okay, so, and if these k numbers have a distribution that is the right one, they match the one in the data, I'm happy. If my outputs, if I run these portfolios on my simulated outputs and on the historical data, I get the same distributions, I'm happy. So the idea is these are the features I care about. So now what we're going to do is that we select, so we select k benchmark strategies, a set of benchmark trading strategies. There can be the strategies employed in your fund or in your bank or whatever you are interested in. For example, some people will be employing, spread trading in bonds. Or some people will be doing index arbitrage on stocks. Or whatever they are doing, they know what they're doing. They're going to specify the strategy, run it across the data, just as they would do a back test of a strategy on any data set. It can be the historical data set or a fictional data set, a hypothetical simulated data set. On each data set, it will generate a profit loss. And what we want is that if they run it across the historical data or on the simulated data created by my generative model, I want to get the same distribution. If I get the same distribution, I'm happy. That's the goal. And now, what does it mean to get, so the this is step one. The features are the profit loss of the portfolios I choose. Step two is now I want to compare these two distributions to see if they are similar. Now they're one-dimensional distributions. I just calculate the profit loss of portfolios. So I have now a one-dimensional distribution for each portfolio. It's the profit loss distribution of the portfolio. How do I compare two one-dimensional distributions to see if they're close? Well, remember, we want to not to lose sight of the tails. So we want to choose a distance between two distributions that is sensitive to the tails. So if you want to be sensitive to the tails, one idea is, well, look at the quantiles. Look at the value at risk of the portfolios. If the value at risk or expected shortfall of the portfolios, these are two common risk measures used for portfolios in risk management. If they are close, then it means that the tails are similar. So that's what we do. So we look at these portfolio losses and we compare the expected shortfall or the value at risk of these portfolios. So here, from this discussion, we can get two ideas. One is, well, for model validation, if you give me a black box, a generative model, how do I check whether this is good for risk management or not? I'm going to judge whether the scenarios are realistic by running some portfolios in this scenarios and looking at the loss distributions and comparing it with the historical loss distributions. And so I'm going to see, for example, if the value at risk from the simulated scenarios, historical scenarios is close. So that's a quantifiable interpretation, a quantifiable model validation criterion. I say if the value at risk is within, 1% or 5% of the historical, it's good. So this is a very concrete thing. So this is for model validation. But now I say, oh, wait, I can also use this for training the model. If I want a model which gives me accurate expected shortfall or value at risk for portfolios, why don't I use this as a training criteria? So that's what we do. So we can actually go back and change the algorithms used for training these networks. We train the model to match some statistical properties of the loss distributions. For example, I can choose to match the quantiles of the loss distribution for a class of benchmark trading strategy specified by the user. If the user says, I do mean reversion trading, or I do momentum trading, or I do, I trade spreads on bonds with these pairs of maturities, okay, fine. I use those strategies and make sure that the model will match the loss distributions for those strategies and gives realistic outputs for those strategies. So what we do is we take these two ideas and put them together. So we use this this training criteria, which matches the tails of loss distributions for a set of benchmark trading strategies, to train neural networks, which then are guaranteed to simulate scenarios which match the tail properties of the benchmark trading strategy that we specify. So that's the idea here. And that's described in the
Rama,
paper.
we still got 5 minutes before
Okay,
the
so
end of the...
so this is the part on scenario simulation. I've just spent the last 5 minutes on describing now how can you use such a scenario simulator. So a scenario simulator, the scenario simulators are used already in risk management extensively for risk calculation of portfolios. So you can just substitute a Monte Carlo engine based on some econometric model by a generative model trained on the same data or some larger data set. So that's one way to use it. But one other way to use this is to say, well, can we also use generative models directly to devise the trading strategy. For example, if I want to build a hedging strategy for an option or for my position, can I learn to hedge from the same data set where I'm learning to generate the scenarios? And the answer is yes. And the idea here is, so the idea is, if we have now a generative model which simulates in a realistic way, let's say we've done that in the previous step, we have learned to simulate realistically the movements of some financial assets, stocks or options and so on. Well, now we can use this generative model to augment the historical data, because we can use the generative model to simulate synthetic scenarios. And the idea is that now we can use this as a tool for calculating hedging strategies in the following way. So let's say I've learned to generate scenarios for price series, which I call S1 to Sn. So these are the risk factors that affect my portfolio. The portfolio can be options, whatever you like. And now what I'm going to do is to say, well, hedging, what is hedging really? Is I have a position, I have a portfolio, the value is pi t. The change in my portfolio, it's delta pi t. The change in the hedging instruments are, the hedging instruments are called HI. The change in the hedging instruments is, I call it delta HI. I want to choose a combination of hedging instruments that matches as closely as possible my position. But if you look at this equation, if you add here an error term, this is a regression equation, because I'm doing a linear combination of the hedging instrument, changes the hedging instruments. So if I can have a sample of the changes in these hedging instruments, if I can have a large enough sample of these, I can just calculate the coefficients here, the hedge ratios, by regression. But normally, I don't have a sample of these, because I want sample of these in the historical data every day. But if I have a generative model which has been trained on these historical data, every day I can use it to generate a sample as large as I want for the variations of all these instruments tomorrow. And then I can say generate a sample of size 10,000 for tomorrow's co-movements in all these prices. And then I have a sample of 10,000 on which I can do a regression. So I can just calculate the hedge ratios by linear regression. I can also include here the transaction costs. It's a little bit more involved, but it will give a L1 term, which leads to what's called the lasso regression in machine learning. But so it's a slight modification. So it means that once we have a generative model, then we can calculate hedge ratios by linear regression, just good old linear regression. And what this linear regression is actually doing, so what does linear regression do? Well, least squares regression minimizes the variance of the difference between the variable you are regressing and the linear combination. So in terms of hedging, it means that it minimizes the hedging error in terms of minimizing the variance of the hedging error. So this is a completely reasonable objective. So linear regression does what you want. It minimizes the variance of the hedging error, in fact, and the regression coefficients will be your hedge ratios. And you can do this every day or every hedging step. You generate one step ahead scenarios with the generative model, you do the regression, and then that's the hedge. So that's the idea. And in the paper, we test this against for option portfolios against well-known hedging methods like delta vega hedging with Black-Scholes model. And so I don't have time to go through that, but basically what we show is that the the model, which is completely blind, it's a data-driven model which just learned from the historical data to just generate scenarios and do regressions. It outperforms delta vega and delta hedging strategies so this is an example where you're hedging certain options on the S&P 500 index with other options and with the underlying index. So you can we show that without retraining the model 3 years out of sample, it still improves over these well-known hedging strategies that are widely used by traders. So that's an example of how these models can be used to design completely data-driven hedging strategies. Data-driven meaning here that from the beginning to the end, there is no assumption on the underlying factors, risk factors, their movements, and so on. It's all based on a machine learning approach where you learn from the data. So you need to have historical data, but you don't need to make any assumptions, and somehow it learns to do the right thing. So I'm not going to go into the table. If you have questions, we can come back to that. So let me stop here and so have time for questions.
Thank you very much, Rama. Thank you. I think we should have another session with you to go deeper on the second aspect. And now I will pass over to Lionel and after to Antoine. Thank you very much.
Yeah, first of all, thanks, Rama, for a fascinating talk. I agree, we should have at least another hour to discuss more in depth. There are a lot of, so I have tons of questions, but I'm going to focus on maybe a couple of questions, and then I'll turn the floor to Antoine, whom I believe also have questions. But okay, the first question I have is a question of scalability, especially when you do simulation. So shall we expect any bottleneck if we look at large portfolios, if we simulate portfolios of, say, hundreds of stocks, 500 stocks, is it going to be a problem at some point in terms of computational power, time? Shall we expect any difficulty or not?
Well, it depends who you are. I mean, if I'm doing this on my laptop, yeah, right. I might run into limitations on my compute power, but I work as an advisor to an investment firm here in London, and they have their own data center.
Sure.
They have their own data center, so the compute power they have is comparable to these large tech firms like like Facebook or Google, so on. So it's that kind of scale. So for those people, that's not a problem really. So scalability depends really on your compute power. These experiments I showed you were done on a laptop. So they go up to 50 stocks and they can be done with options. The number of options is very high. So we use the S&P option surface. You have around 1,000 options now being.
Okay.
So that's the kind of thing that we can do. It's the training is the heavy computational stuff, but remember the training is done offline. So the training is you do it on some large computer, but when you want to run it on a daily basis for hedging, that's really fast. That's forward.
You don't need to redo it again.
Yeah. So somebody trains it in the basement, then you are the trader, you click and it runs instantaneously. So that's the quick answer.
Okay, great, thanks. That makes total sense. So it's definitely practical, and from what I hear, people are actually using. So yeah, that makes total sense. I guess my second question has something to do with, okay, you can apply your methodology not only to variance minimization for option replication, but you could do mean variance analysis, right? And I think you mentioned that.
Mean variance you can do,
yeah. So you mentioned that in the paper. Now, the way I see it is because the process moves forward in time step by step, it sounds like you are only looking, I mean, you have to be looking at a myopic strategy.
Yes. It's right? Next day, it's 1 day ahead hedging.
It's a 1 day ahead hedging, right? So if you think about, dynamic asset allocation models where, in the old-fashioned way where we do backward induction, stochastic control, and so on and so forth.
Exactly.
Then we have this intertemporal hedging demand that
Uh-huh.
makes the strategy non-myopic and kind of
Yes.
smarter at taking into account horizon. So is there any way that your methodology can
Yes,
account
this
for
is
these
not
things?
doing that. Exactly.
It's not.
It's a
Yes.
very good point.
Okay.
This is not doing that. So the generative model is giving you a device to generate next day scenarios. You could use it to generate 2-day scenarios, 3-day scenarios, but you're going to generate forward looking. You're going to generate this going forward.
Mm-hmm.
There is it's the opposite of model-based hedging or model-based optimal investment strategies, where you assume you know the model describing the dynamics up to the horizon, and then you move backward from the horizon. There's no such assumption here.
Yes.
We don't know anything about what's going on at the horizon. And so this is a key difference, yeah.
Okay, I understand. So there
Now
wouldn't
you
be
can
any.
ask the following question. You can ask, if I do this myopic thing, what am I optimizing globally? Am I optimizing something globally or not? In general, no, because it's not time consistent.
Yeah, exactly. So okay, so we might be losing the access to these intertemporal hedging demand effects or horizon dependent effects.
Yeah.
I don't know if there's a way to, by the way, capture them somehow.
Well, I would say if you know the distribution of all your variables up to the horizon, use that. You don't need a generative model.
Yeah, right.
You need a generative model because you don't know the
Sure.
distribution of these risk factors, and somehow that's what it's doing. So this is a bit like same idea in reinforcement learning literature. So reinforcement learning compared to stochastic control is reinforcement. Stochastic control, you know the true dynamics, you optimize something. In reinforcement learning, you have data, but you don't know anything. You just learn on the fly. So this is learning on the fly.
Yeah, thanks. That makes sense. So the trade-off is, as usual, then you're going to get a more realistic scenarios. But if you go the parametric way, then your scenarios will not be very realistic. But then you can do many things. But of course, you're running that risk. Thank you so much. Let me turn the floor to Antoine. I know Antoine has questions on his own.
Yes, thank you, Lionel. And thank you, Rama CONT. It was a great presentation. I have a question regarding the choice you made of not retraining the model during 4 years through your testing period. I was wondering, maybe retraining the model on a regular basis would probably, do you think it would have avoided you to segregate the COVID crisis data through your analysis?
No, the COVID crisis, I haven't seen a model which, performs well during the COVID crisis. It was so different. And these models are not magic, basically they are uncovering some statistical regularities which are too complicated for us to parameterize with the function, but they have to be there. So the fundamental assumption in all these learning models, machine learning or otherwise, is that there's some stationarity. If there's no stationarity, if what's going to happen next week is fundamentally different from last week or last year or last month, well, statistical models and machine learning models are not going to do you any good. So there is a hidden assumption of stationarity. So during COVID, none of these things worked. Delta hedging didn't work. Vega hedging didn't work. This one didn't work. Nothing worked. It was really an outlier in any sense of the term.
Okay. And
because it was driven by non-financial factors. They were not in the data. There's no instance of it.
Okay, so there is no need to retrain a model on a regular basis, like monthly or annual basis.
I mean, you could retrain, but I'm just saying this won't solve the COVID problem. Even if you retrained it the day before COVID, it wouldn't fix the problem. That's what I'm saying.
Okay,
but you could, in general, I don't Yeah, it's true. This is people think that they need to retrain all the time the models, recalibrate everything every day. That's what they do in that's what people do in the industry because they think somehow nothing is stationary, so you have to retrain. But there's something a little bit subtle here, because we are not saying that the data is stationary, but the neural network is learning the relation between the inputs and the outputs. We are assuming that relation is stationary. If the inputs are non-stationary, the outputs will be non-stationary. But the relation is what we assume is stationary. So this is a little bit different. And when we don't retrain for 4 years, and we get good results, I would say this supports this assumption.
Okay. Okay, thank you very much.
Okay, perhaps
But
time
this is
for
an important
another
question.
question, Antoine, and before we close the session.
It was it for me. Thank you very much.
Okay. So I think we should plan another session. Rama, it was really a great and very stimulating talk. So thank you again, Rama. Thanks to Lionel. Thanks to Antoine. Before we close this session, I just want to say that we will be back for end of November, and this will be a different topic. We'll talk about the evolution of the perceived cost of capital for green films, and this will be with Niels Gorsman from Chicago booth. So thank you very much, and see you soon. Merci beaucoup. Thanks.
Thank you. Thank you, Rama.
Thank you, Rama.
Thank you.
Thanks.